EEL6825. My name is Brittany English, and today I will be teaching you all about eigenface. Eigenface is a facial recognition algorithm that uses the basic principles of linear algebra to perform facial recognition. It creates orthonormal bases in the face space off of the images. So it reads them in, it creates eigenvectors and eigenvalues, and creates all these orthonormal bases that we can later project and compare it onto. So for the algorithm, how we execute this is first we define a training set of images. So just read in some images. 2, we will calculate the average training set image, and then you subtract the average from all the images. And that just kind of gets them all so that they're similar to one another. So you're just removing that average. Very simple. And then step 3, we calculate the eigenfaces of the training set using n eigenvalues in free space, and we get to define n to be whatever we want. And 4, calculate the distribution of clusters within the free space by calculating the distance between images, or the weights in the face space. So now that means that once we've projected all of our images onto face space, if we look at it visually, there will be clusters, and we will keep the all the images of a person is going to fall in that same cluster. So we'll kind of calculate out where those clusters happen and notice where they are. Then 5, we'll define those clusters to correspond to the test subject. Then 6, we will acquire new images. And 7, we will project each of the new images into free space. And then 8, we'll calculate those distances and figure out which cluster our image fell into. So for our first step, we're calculating that image. If you look at this formula here, it's just simply an averaging function where our gamma here is our list of all of our images in the training set. And then we subtract that average here from each of the images, and then that will make a new image that doesn't have the average. And in my training set, this is what the average face looked like. And if you can see, it does have some details into it. You can see the head shape, you can see some hair, you can see ears, you can see eyes and nose and mouth. So it is interesting that the average face has all of these different attributes to it. Next, we will calculate the eigenfaces. Normally, we would calculate our C matrix here, which is orthonormal bases, using a very large square matrix that has sides the size of an image. So for every pixel in the image, there's a line in that matrices. So it's a huge matrix, and this is how we could get things almost perfectly when we project them back. Well, however, that is very computationally heavy, so we don't really want to do that. So we're going to calculate L, which will be orthonormal bases using a much smaller square matrix that has sides the number of images in your training matrix. So let's say you have, for example, 10 test subjects, and let's say, oops, I need to go back. Let's say you have 5 of your images in that training matrix for each person. So then that would give you a total of 50 images. So this matrix here would have 50 lines in it, which is much better than this, which could have, tens of thousands of lines, depending on how big your image resolution is, and that's a pretty small image resolution. So anyway, L is computationally better. Now we're going to apply the definition of eigenvector to L. So our LV equals lambda V. Then we're going to apply the definition of L, which is right here, to here, plug it in, and then we'll get this formula. And next we're going to multiply both sides by A, so just put that A out in front. And then we're going to move the scalar, because lambda is a scalar, out in front on this side. And then when we add parentheses around these, we're able to see that AV is an eigenvector of C by the definition of eigenvector, because this here is C, and we've got our lambda, and now we just have AV. So, because this is true, we can use this L vector, and it will be able to be similar to C, similar enough to use. So, from that we get all of our eigenfaces. And over here I have plotted some of our eigenfaces. They look kind of spooky and ghost-like, but you can see each of them has different accentuated attributes. You can see this guy's bald, this guy's bald, this guy has hair. You can see this guy kind of has a beard and some facial hair. There's some glasses in there. Everybody has noses and eyes. And if you look at the face shapes are different, the bone structures are different. And I've really noticed this algorithm focuses more on the face shape and the bone structure than it does on things like eyes and mouth, like the standard attributes that we focus on with our eyes. It is also interesting to note that the eigenfaces that we select are the ones that have the largest eigenvalues, so they're the most strongly prominent attributes of the faces. So next we'll calculate the feature vector, and the feature vector is calculated just with this formula here, where omega is our feature vector, and all of these here are just our eigenvalues, and then that's our image. So you just multiply all the eigenvalues by the image, and that kind of projects your image into that face space, or makes your feature vector. So here are some examples of projecting an original image to that feature vector. And this image was inside our training matrix. So if you look, they're very, very similar, but there is some subtle differences. Especially it's a lot more grainy if you notice, kind of in his cheeks over here and around his nose. It's more grainy and a little bit darker. But other than that, he looks almost perfectly matched, which is very good. But this here is, we can tell visually that that's the same guy as before, but this was an image that was outside of our training matrix. And when we project it back onto our feature vectors, you can kind of see that it gets really blurred and it's difficult to tell. And visually, you might not be able to confirm that this is in fact our same test subject here, because the eyes, are kind of gone, the nose is weak, the mouth is weak. But if you really look at the bone structure and the shape of the face, you notice it's all there, and the ears are very similar. And that's what our algorithm looks at more than the features. And one thing you notice is if you put your computer screen really far away from you, or if you kind of squint your eyes where everything gets blurry, visually these images do look similar to us. They're just much lower resolution than we're used to looking at, and this one's much blurrier. But if we were looking at smaller, farther away, where our mind blurred our original over here, we would think that they were similar as well. And so that's kind of the level of similarities that our eigenface algorithm's looking at. So now we'll talk about how we classify these. As I said before, when this is a projection, a rough projection, an estimate of what we would see projected into two-dimensional space. Obviously, with face space, it's going to be many, many, many dimensions. But as I said before, when you project things into our face space, you kind of notice that things are going to cluster like these gray blobs are. And you're going to notice that, there are things that very obviously go together and things that don't. So we would find the distance for our farthest distance here, and we define that as our radius. We'd find our center point, and we'd make a circle around it. And we would make a circle around every single